Right, so hello everybody. Welcome to Philosophy of Physics Week 2. We have a wonderful lineup this term, but few can be quite so exalting as Julian Barbour. He's someone who needs no introduction, but you know how those cliches go. I'm going to do it anyway. So Julian has worked independently in every sense of the word and has, I think, single-handedly substantially transformed a lot of people's understanding of the nature of time, and with it of gravity and dynamics. The writer of two extraordinary books. One is Absolute and Relative Motion, which is a very big book and a masterpiece of historical, the time, disappearance of time. The end of time. A very different sort of book, but again, a lovely and wonderful book. I think Julian has really been pioneering shape dynamics for the last 15 or 20 years. He and I have great affinities going back to a mutual love of Leibniz, which doesn't mean we agree about everything, but we agree about a great deal. Julian, welcome. Thank you for coming, and take over, please. The screen is yours.
All right. There seem to be other people, and I saw Enrique Gomez.
Yes, I know, but that's all right. If you come in front of the camera, you'll be there.
Well, it's a great pleasure to be here. Not the first time, and perhaps not the last. Just the Latin tag, formicum formosa, means beautiful shape. No, nothing is happening. Ah, here we are. So I'll just leave people to look at that. I've had really tremendous collaboration with people. Recently, things have got firmed up by a long weekend I had a couple of weeks ago with Tim Kozlowski and Flavio Mercati. And there's a great book by Flavio on shape dynamics. And there's going to be a slide you're going to see quite a lot of times because I think it's very impressive, by Manuel Izquierdo. So, right, let's just start with the notion of configuration spaces, which really goes back to Leibniz. Where are my triangles gone? Oh, here they are. So, according to Newton, if there are three particles at the vertices of the triangle, they have separations, but they can also be anywhere in space. And that's the Newtonian configuration space for n particles, 3n dimensions. You could put them all relative to the center of mass, and that's got 3 less dimensions. But the one that's really relevant for Leibnizian ideas is the relative configuration space, where you say all that counts is just the separations between the particles. Are people seeing that, perhaps?
Yeah, they're seeing fine.
Yeah. And that's got 3n minus 6 dimensions. So really space has disappeared then, and all you have is what Leibniz said, the order of coexisting things, the distances between them. And then one more step, which has really come very late in this story of Machian dynamics, is to say, well, if the 3 particles are the whole universe, what does it mean to say how large the triangle is? That presupposes a measuring rod outside the universe, and that's nonsense. So you really should take out scale as well, and then you come down to shape space. That's, in the case of 3 particles, that's only got 2 dimensions. It's 3n minus 7 in general. And this is all done with the fundamental symmetry group of Euclidean space, the similarity group. So wait a minute, how did I? Oh, it's over here, going down. So what you can do without losing any information and getting rid of all redundancy is project general Newtonian solutions of the n-body problem to shape space. And then you just get a curve in shape space. It's not got any parameter. It doesn't tell you how time is flowing, and it doesn't tell you which is the direction of time, but it hasn't lost any of the valuable information. Now, if you take a general Newtonian solution, how can you express it in shape space? Now, the natural variables in shape space, they're the ones that define a shape. That's 3n minus 7 of them. And then a direction in shape space, you only need 1 less for that. So it's 3n minus 8. Now, if you project general Newtonian solutions to shape space, and to describe them, you find you need 5 extra quantities. They are the ratio these are dimensionless quantities. They have a profound effect on Newtonian evolution, but you can't encode them in a shape and a direction in shape space. So they are the ratio of the kinetic energy divided by the potential energy. They're the ratio of the amount of kinetic energy in rotation divided by the amount in change of shape. They're also the amount in overall expansion, dilation, divided by the amount in change of shape. And then you also have two numbers which define the direction of the angular momentum relative to the instantaneous shape. So those are 5 things. They're all in Newtonian theory, and they are, from relationist point of view, Leibniz and I hope Simon, they're anathema because they come from Newton's use of absolute space. Now, if the energy and the angular momentum are 0, and there are very strong reasons for arguing that on Machian grounds, then 4 of them disappear. The one to do with the ratio of the kinetic to the potential energy, the angular momentum part, its direction and its magnitude. And that just leaves one, which is the ratio of the amount of kinetic energy in overall dilation, expansion, divided by the amount of change of shape. And I'm going to suggest and argue that this is by far the most important pure number in physics. So just to give you the idea of how one gets rid and formulates dynamics without it, basically the idea which was developed by Bruno Bertotti and myself back in the 70s and early 80s is best matching. You need somehow to define an action using only, first of all, with leaving in size, how much action there is between 2 triangles. They're not congruent, so you try and bring them to best overlap, and you can't do that because they're incongruent. And you get left over, here's particle 1, there's the distance between it in the best matched position. So you take that distance, multiply, square it, and multiply by the mass. You do that for each 3 particles, or for as many as you've got, and that gives you a quantity which, in the limit, is going to be defining the action. And with that, you can then define a geodesic theory in the relative configuration space, and the action is my second one there. This is just the equivalent of Newtonian motion, of inertial motion in the relative configuration space. So that's what I would call a natural metric on the relative configuration space. And then you can now go to shape space, where you see you divide the. Will people see me if I walk over here? I don't know. You define the Newtonian kinetic metric by the center of mass moment of inertia, which is defined here. And then you minimize this with respect to translations, rotations, and dilatations. And that actually defines the distance between those 2 shapes. And it defines a natural metric in shape space. And I'm going to suggest that that is really the bedrock of the theory. And if you look up the etymology of perfect, it comes from perficere, to complete. I would say this is the completion of relational dynamics to get down to that stage. And I'm already talking so much. Where's my water supply gone? Did I?
It's right there.
But here, yes. Where's my mug? That's somebody's pinched it.
I did leave it just here.
Yes, I know it was there, and it's gone. Right. Splendid. Next one. So the Machian dynamics, I've really already explained that. So you have the Sorry, are people seeing me when I walk over?
No, they don't.
They don't.
If you use the trackpad, I think you can point to it. Try it.
Is that showing up? No, it doesn't. Anyway, the first equation gives you the action principle to define. This defines a geodesic on the relative configuration space and it has zero energy. And it leads to, it implements Mach's principle in the relative configuration space. You have a constraint which says that the Hamiltonian, the total energy is zero. The potential energy is the Newtonian potential energy. It says that the total momentum is zero and the total angular momentum is zero. And the key thing here is that the Newtonian gravitational potential is an invariant of the Euclidean group, and that ensures that the vanishing of the total momentum and the total angular momentum propagate. So that's good news. And in addition, because time doesn't appear in all of this, the constraint that the total energy vanishes, that also propagates. And now you can do exactly the same thing on shape space, but this is where the real mystery comes. So the key thing here is you need a potential which is not only invariant under the Euclidean group, but it's invariant under the similarity group. So you've got to have something that's dimensionless, does not change under scaling. So to get that, you multiply the Newton potential by the square root of the moment of inertia. And that is a dimensionless quantity. And that gives you then a Machian action on shape space. And it implements Mach's principle with the old constraints, but a new one. It's not in bold there because it's a scalar quantity. It's D for the dilatational momentum, So this is the exact analog of angular momentum. It has the same dimensions, but it's a measure of how much is in overall expansion. And that quantity vanishes. And as I say, it's the analog of angular momentum. So because so that shape potential, which is the dimensionless form of the Newton potential, because it's an invariant of the similarity group, and because the Hamiltonian vanishes, those two conditions together ensure that the constraint that the dilatational momentum vanishes propagates. So that's guaranteed. Now we come to the two great problems of quantum gravity. The first is the problem of time. In canonical quantum gravity on the relative configuration space, and by the way, very closely analogous things go through to general relativity with curved three-dimensional geometry. If you just try and quantize in the standard way, the Hamiltonian that vanishes, you get a static wave function. Nothing seems to happen. They're just probabilities for shapes. And that problem was recognized 60 years ago, and all the attempts to define an internal time and get around that problem, nobody's been persuaded that that has succeeded so far. Now, I think an even more striking problem is the one that if we go to shape space, the fact that the dilatational momentum, which is half the time derivative of the moment of inertia, that vanishes. And that means in such a universe, you can have no expansion of the universe. It just goes round and round in Poincare recurrent loops in geodesics. So geodesic theories on the compact shape space. It's very important that shape space is compact. That's going to be key. And so they're Poincare recurrent. So it's not quite true what I've said here, that the problem of scale has not hitherto been recognized in quantum gravity. It hasn't been recognized in the way I present the things, but there has been a lot of concern about trying to quantize conformal gravity and the conformal invariance of general relativity. Roger Penrose here in Oxford has thought a lot about it. So that statement I make there is not quite true, but that hasn't really led to any satisfactory suggestion. So what I'm going to suggest is that perhaps the two problems need to be solved together, and that one may succeed in killing two birds with one stone. So I'm going to suggest that the stone is the complexity, which is just the name that my collaborators Kozlowski, Mercati, and I with me, we introduced to describe that thing that I called earlier the shape potential. That's the name. So that Newton potential, which is at the bottom in the third equation on this slide, the Newton potential made scale invariant. The n-body specialists call it either the shape potential or the normalized Newton potential. For reasons that I will explain, we call it the complexity. Now, it's very interesting. It's the ratio of, as it's dimensionless, it's the ratio of two lengths, which makes it dimensionless. And also the mass is taken out, so it's a pure number. So the root mean square length is basically if you have a collection of points in Euclidean space, the root mean square length is the average of the long separations between the particles. And that's, Leibniz showed that it's actually essentially, it's equivalent, identically equal to the square root of the center of mass moment of inertia. And then the other basic length that stares out at you is the mean harmonic length, and that's the inverse of the Newton potential. So now you take the ratio of that, the root mean square length divided by the mean harmonic length, that's up to the sign, and a power of the total mass, it's what the n-body people call the shape potential. And it's, as I say, it's the Newton potential made scale invariant by multiplying by the square root of the moment of inertia. Now down at the bottom, that's a picture of the shape sphere. Because a triangle has three sides, but its shape is defined by two internal angles, the great joy of shape dynamics is you can represent the first non-trivial problem visually, beautifully on the surface of a sphere. So each point on the sphere is the shape of a triangle. Mirror symmetric triangles are with the same are at the same latitude, are in the northern and southern hemisphere. The collinear triangles, the limiting case of collinear triangles, are on the equator, and there are 6 special points. There are 3 points, binary coincidences, where 2 particles get, literally coincide or get very close to each other compared with the third. And then there are 3 other points, which are called the Euler configurations, and I'll explain why in a moment. And they are saddle points of the complexity. The complexity is shown by the shading there. Now, in the 3-body problem, the complexity always has an absolute minimum at the equilateral triangle, whatever the mass is. And then it has 3 saddle points on the equator, these Euler points. And the complexity rises to infinitely high peaks at the 2-body collisions. So now the complexity, I'm going to stick my neck out. I think the complexity might just be the secret of the universe. Now that's a big claim, but I'm going to argue why. Well, first of all, and this is why we call it the complexity, is it's a measure of clustering or variety. Simon has mentioned our joint enthusiasm for Leibniz. Leibniz was always saying, variety is the only way you can sort of say anything about the universe. If there's no variety, you can't really say anything. So it's very fundamental at the epistemological level. You've already heard that it's minus the dimensionless shape potential. Now, this is a thing which is very interesting, is that it's the intrinsic size of any shape. Because how do you measure something? You take a ruler and you say, this is my unit of length, and now I lay it on the thing I want to measure. So going across the desk, it's about 5 times my ruler. So you measure a longer interval with a shorter interval. So what is the scale invariant size of a cluster of points? We'll say they all have equal mass. Well, you just divide the root mean square length by the mean harmonic length, and that is the scale invariant size. So I'm just going to illustrate that on that basis. So we're inside the universe. We have to measure, the size of the universe is measured relative to me. And if it's a universe of just 3 particles, this triangle, despite appearances, is actually smaller than that one, because the ratio of the shortest side to the longest side is greater in that one than that. So you have to get rid of the notion of size, and it's incredibly difficult to do it. Now, Poincaré pointed this out, how mysterious it was, but what he didn't consider was what happens when the shape changes. That's when things get really interesting. So just to bring the point home, compared with those 2 universes, they are tiny compared with this. This is vastly bigger than those for Alice in Wonderland creatures who live inside this universe, because that side is much shorter than that side. So get that into your minds. That is how you measure the size of the universe. Now, interestingly, this is very strange, because the principle of least action and the whole of both Newtonian and Einsteinian dynamics, you specify a ratio of sizes at the 2 ends of the integration of the action. So why on earth, when actually there's an intrinsic notion of size in a shape, does it play such a fundamental role in both Newtonian and Einsteinian dynamics? And finally, this quantity, it's a pure number that characterizes the whole universe in a way that the Planck units don't, because they rely on a particular choice of units. So there's something very fundamental about it. Now, the complexity is actually what defines the arrow of time. I'm going to assert that it's the complexity of the evolving universe, not entropy, which fundamentally determines the direction. The entropic arrow of time is a subsidiary one, which comes out of something I'm going to point out now. So if the energy is greater than or equal to 0, and in a Machian universe, you're going to expect the energy to be exactly 0, then except in 0 measure cases, which I'll come to and are very interesting indeed, the size of the universe, the Newtonian universe, in the infinite Newtonian past, the moment of inertia is infinitely great. It comes down to a finite minimum and then rises to an absolute, goes up to infinity again. And that was discovered by Lagrange in 1772. The proof is done in two lines. It's a very simple proof. And that has very profound consequences. First of all, because the dilatational momentum, is the time derivative of the size of the universe, the moment of inertia, that's monotonic. It goes from minus infinity to plus infinity in either direction of time. And that means there is no Poincaré recurrence. Now, Poincaré recurrence is the real reason why Boltzmann could not explain the entropic arrow of time. It was Poincaré recurrence in the famous debate with Sermolo. So, and that was because he presupposed a system in a box, which had a phase space of bounded Liouville measure. The Newtonian n-body problem does not have a bounded phase space. It has an unbounded phase space. The way you should think about statistics and the arrow of time is completely and utterly different in the Newtonian n-body problem, and I strongly believe it is going to prove to be so in the case of the universe described by general relativity. So what happens? So this is a plot of what the complexity does. This is a simulation, a numerical simulation with 1,000 particles. The dip at the bottom is around at this, what we call the Janus point, and there are bidirectional arrows of time that go out in both directions from it. And they are a direct consequence of the law of nature. That is not a past hypothesis assumption just put in desperately to explain the arrow of time. It is there straight as a consequence of Newton's laws of motion. There's no nonsense about that. And on the right, down below, you see a sort of an artistic impression of what is happening. At the Janus point, typically, the particles are moving around rather randomly, and they make a uniform thing, rather like a swarm of bees. I think that can be proved rigorously. It's a delicate proof, but certainly there's a lot of evidence that that's the case, and certainly there's a vast number of solutions where that happens. And then as you go out in both directions from the Janus point, clusters form, including above all Kepler pairs, which become absolutely perfect, ever better rods, clocks, and compasses all in one. And all those clocks that form out on either side from the Janus point, they all march in step. They're all in phase with each other. You go from disorder at the Janus point to ever better perfect order as you go out. This is the complete inversion of the normal story of the universe going from order to disorder. And it comes straight out of the Newtonian n-body problem. Now, where entropy comes into this is when subsystems form, because the mere fact that the complexity is increasing says that subsystems are forming. And as they form with a lower, and they exist transiently, they come into existence and they go out of existence, and that birth and death is aligned with the growth of complexity. And while they exist, they are subject to the virial theorem. They virialize for a certain length of time, and then they are like thermodynamic systems. So thermodynamics is emergent in this story. It's transient in systems that form transiently. So that's quite a big change in the picture. So the way really to think about Newtonian theory is to take scale out of it. You can solve the Hamiltonian constraint for the size of the universe, and then you just get something which is expressed in terms of shape degrees of freedom. There's one extra one because of that one extra one that comes in through the Newtonian theory. So the evolution in shape space is determined by the shape, the direction in which the shape is changing, and one extra degree of freedom. And it's a degree of freedom, which Leibniz would love this. It's putting a striving into the universe. The universe is always striving to bend away from the natural geodesic in shape space and climb up to higher complexity. And you see it in this diagram here. You see the Janus point, you may not be able to see it, is a white square at the back of the shape sphere. And then the two branches of the solution go off in opposite directions. And you see how they climb up that mountain of the complexity. And as they go up there, that's where a Kepler pair forms. It's a Kepler pair forming and a singleton going off in the other direction. And relative to the clock, rod, and compass that the Kepler pair forms, the singleton is going off and is obeying Newton's first law. So it's an absolute perfect example of order being created out of chaos. And if you try and set up the solution and run it back from where the Kepler pairs formed, when it gets near the Janus point, that's a total scrambler. It becomes chaotic there, and you can't tell what will happen on the other half. But you know if the energy and the angular momentum are zero, every single solution, except for this zero measure set to which I'm coming, will be forming a Kepler pair and a singleton. So I do love this expression, WYSIWYG. What you see is what you get. So there in that picture that you see there, that is the deep truth of Newtonian theory. It is completely wrong to say that Newtonian theory is a theory of clockwork that made it so hated by people like William Blake. It's not clockwork, but it's the creation of order out of disorder. And that order includes the creation of rods and synchronized clockwork. So it doesn't just describe clockwork, it describes how the clockwork is created and then continues to describe how that clockwork runs once it's been created. So as I say, it's a classic example, I would say, of Leibniz's idea that the universe is striving. And this is going to lead to a sea change in statistical mechanics. So here's this great quote from Maxwell. The true logic of this world is the calculus of probabilities, which takes account of the magnitude of the probability. Now, I said it's a sea change. Now, the natural metric, which is just actually defining distances in shape space, this is all that remains of kinetic energy. Kinetic energy just goes out of the statistical mechanics of the universe if this picture is right. And what instead in its place you get is it defines the measure for the probability of shapes. And you'll see this in a very dramatic form. And this is going to be the probability, the calculus, which takes account of the magnitude of the probability. It is a gift of shape space. You take out scale and you're given perfect, rigorous probability measure. And you can do that because shape space is compact. You've got something which tells, so you can give it a nominal volume. You can then say, what is the ratio of the size, the volume of a region within shape space compared with the total. And even more interesting is that we see, we're going to foliate shape space by the values of the shape of the complexity, the shape complexity, and the same will hold there. The shape complexity, it's multidimensional. Well, it's one-dimensional in the three-body problem. It's those contour lines there. And the shape potential, the measure in that on the shape sphere is just the length along the contour. That is the measure. And I don't think you can ask for anything which is more rigorous than that. There's no coarse graining, no fishy saying it's a confined system and you're not sure how long it's going to stay confined or anything there. So that's the magnitude of the probability which Maxwell says we need. And that's the measure. We've got it there. So there's going to be a primary state function, and that's going to be the shape complexity. And then a second one we'll come to is going to be a Shannon entropy of the shapes. I'll come to that. That will require some coarse graining. I think it's possible maybe one can do it without coarse graining, but already with coarse graining, it's going to be interesting. So now, the extrema of the complexity or the shape potential are extraordinarily interesting. Just make a note of the three references that I put there. There's a wonderful paper by Donald Sari who talks, I'll tell you in a moment what central configurations are, but he quotes the mathematician Stephen Smale saying that the study of central configurations is a problem for the 21st century. I hope you'll agree with me by the time I finish this talk. There are two lovely papers. One is by Richard Batty, Gary Gibbons, and Paul Sutcliffe, and another by George Ellis and Gary Gibbons, which I strongly recommend to read. Now, a central configuration, its significance was recognized in the late 19th century. It's a configuration in which the force that every particle in the system acts on each individual particle is such that that force is directed towards the center of mass, and the strength of the force grows the further the particle is away from the center of mass. So if the particles start off in a central configuration at rest, they will fall without the shape changing until they all collide in an instant at the center of mass. And that's called a total explosion. And people started studying these things in the 19th century. Now that example I gave where the shape does not change, that's a homothetic total collision. Vastly more interesting are Newtonian, highly non-trivial Newtonian n-body solutions in which the shape does change until they actually get to the shape which is a central configuration, which satisfies where the shape satisfies that condition, and then they collide at that point. And n-body specialists have not found any way to continue the motion beyond such a total collision. So that's the end of the story, going at it that way. Now, in 2 dimensions, instead of them falling to rest, you can have what's called balanced motion, where if the system is rotating, the centrifugal force balances the gravitational force. And Euler was the first person who realized this with the collinear Euler configurations. And he pointed out that if the moon was 3 times further from the Earth than it currently is, and it was on a line Sun, Earth, Moon, we would see the moon full forever. It would stay there forever. And then Lagrange discovered the same sort of property with the equilateral triangle, which is at the absolute minimum of the shape potential. Then I don't know whether he thought about it, but certainly it was realized, somebody realized that there ought to be asteroids forming equilateral triangles with the Sun, Earth, and this asteroid going around on the Earth's orbit. And indeed, they were looked for and they were found on both ahead of the Earth and behind the Earth in its orbit. These are the Trojan asteroids. So this was, a great discovery there. So now these, under the James Webb telescope, is now sitting at one which is at a Lagrange point with the Earth and the Moon. It's right at the heart of Newtonian gravity. Now, these central configurations, there's an incredible number of them. Basically, they're at least n factorial. And they have the absolutely beautiful, and at least one of them, and maybe a unique one, if the masses are all unequal, then I think I'm virtually certain, unless it was a great fluke, there will be one shape which has the absolute minimum. And it's a beautiful consequence of Newton's potential theorem, the famous one that Newton was so proud about, that when you have lots of particles and the complexity is low, they form an almost perfect uniform sphere. And this is the calculation, numerical calculation in the paper by Batty, Gibbons, and Sutcliffe. It's just incredible. That's Newton for you. And so there's a slice through it shown on the right there. So the equilateral triangle, by the way, the equilateral triangle is the smallest mathematical universe because all the sides are equal. By my internal measurement, it's the smallest universe. The regular tetrahedron is also has that property of having the absolute minimum of the complexity. Let me take a bit more water. So now you can, because you can reverse the time, a total collision is also a total explosion. It's a Newtonian Big Bang. They come out of what seems to be a zero size, but if size it isn't kosher in shape dynamics, you mustn't think about size, you must think about shape. So actually it starts with a very uniform shape, and then the shape just gets more structured and clusters form, Kepler pairs form and so forth there. Now, this nature of total collisions and total explosions is very special. And this is where you see again that the shape potential, the scale invariant form of the Newtonian potential is decisive, because it's very interesting. In the three-body problem, if the masses are not all equal, then the shape potential has a, oh crikey, what's it called? What's the second derivatives? I'm getting so bad with remembering names. Come on, the thing that determines, that has eigenvectors and determines the second derivatives. Anyway, it'll come. I heard it, yeah, what was it? Hessian. The Hessian, thank you. The Hessian is what determines it. So if the Hessian has the largest eigenvalue, and it will if the masses are all unequal, virtually all these solutions will either come in or go out along that one there. And if however many particles there are, as long as there's one with a maximum eigenvalue, the great bulk of them go out there. And then they splay out, as you see there. So this is, again, shape is everything. It really is, if we're talking about modeling the universe. Now, even more interesting, so the total collision can only happen if the angular momentum is zero. Even more interesting is what's called parabolic escape. This is where the particles all manage to escape to infinity from some general initial condition, if it's a very special one. And when they get there, they are in the shape of a central configuration, and all the particles have come to rest. And that is only possible if both the angular momentum and the energy are exactly zero. So those are very, very special solutions. And when you take the time reverse of them in shape space, you just have a curve in shape space which goes from a central configuration out into shape space somewhere and wanders off through shape space. But it starts at that very special point. And this is going to be very important in my argument in a moment. So now the question is, are there any Newtonian solutions which are completely free of Newton's absolutes? And I said this great problem was that if you just plot the Newtonian solutions in shape space, you've got this one extra degree of freedom. I call it the anomaly or the creation measure, because it's the thing that is causing all the structure to be formed, this one extra number. And that really reflects the fact that in Newtonian theory, you have a ratio of overall kinetic energy and overall expansion divided by the amount of change of shape. But now there's some very interesting, so I'm going to say, let us assume that there is a central configuration that has the absolute minimum of the shape potential. Let me call it alpha for rather obvious reasons. And a good Leibnizian like Simon and myself will say the principle of sufficient reason suggests, well, we call it alpha, and then what's going to happen if we say we're only interested in the solutions that come out of alpha or go into alpha? Now, given the curve in shape space, you can reconstruct the Newtonian solution that generated it, that you projected it to shape space. Now, when you actually do that with a parabolic escape solution, and you look at the point where it starts and you say, what is the value of the Newton's size there, the moment of inertia? How large is the moment of inertia at that point, alpha, which corresponds, if you see it as a parabolic escape, there the size is infinitely great. If you see it as a total explosion, which in shape space is indistinguishable, we're pretty certain about that. We're pretty certain it's indistinguishable. There's a size is absolutely zero. So my conjecture is that the solutions that come in to or come out of alpha, they are governed by Newton's equations. They're governed by the Newton potential, They create all that wonderful structure that Newton does, but they don't carry the original sin of Newton's absolutes. That's my conjecture. And there's an extraordinarily interesting set of such solutions, which I'll come to in a moment. So now I'm going to come to the most outrageous suggestion. I've explained how much that complexity does, and I've shown you how complexity is what determines the direction of time. I'm now going to suggest that we should literally say complexity is time. So if we have n particles in Euclidean space, they will always form a shape. Look at the value of the shape potential, and I would let us say that is time. Now, it will run backwards in some Newtonian solutions. You saw it goes backwards and forwards, but it always is striving to increase. But for a large number of particles, as the number of particles goes up, I think it's going to be very rare. It's going to be very hard to find solutions where it runs backwards. So, the complexity depends on two things, which is going to be very important. One, it depends upon the ratios of the separations between the particles, but it also increases with the number of particles. So I'm going to consider shapes, models of possible instantaneous shapes of universes of ever more particles that have a given value of the complexity. So I'm going to foliate shape space by isocomplexity surfaces, and you see that here. And take the value of the complexity and subtract its minimal value, and we're going to say that is the date stamp of each shape. So now these figures here have come out of shape dynamics and me talking to a very high-powered n-body specialist in Paris, Alain Albouy, and he got interested in the idea of seeing what these solutions look like, numerical solutions that look like as they come out of a total explosion. That's a very difficult problem, but what he did, for a few months he had a Spanish student, Manuel Izquierdo, finding the shapes of central configurations. And this shows here, one on the left, now it's in 2 dimensions, so the density is not quite uniform. It would be in 3 dimensions, and they look exactly the same in 3 dimensions, but they take vastly longer to calculate. So the one on the left is either exactly at the absolute minimum of the complexity. This is 1,000 equal mass particles, or it's very close to it. And the one on the right is only 0.5% larger in its complexity, but just look at the structure. And this was actually a very interesting discovery. Nobody before this had realized. Hitherto, when people had been looking to find central configurations, they'd either done what that paper by Batty, Gibbons and Sutcliffe and looked for ones very near the absolute minimum. So they found lots like the one on the left, or they did exhaustive searches for up to about 10 particles, and there's still several, because it's 10 factorial. So we're talking about thousands of central configurations if you have 10 particles. And they began to find beginnings of these incredible voids and filaments. But these central configurations that Manuel found it's a discovery. And it's thanks to the obsession of reshaped dynamicists. And just look at it, it's quite extraordinary. Now, just imagine if this is in 2 dimensions, so you could have these balanced things, you could let them rotate with a certain angular momentum, and every 1,000 particles there would all, in a tremendous ballet, come in and out, breathing in elliptical motions around the center of mass. Online, you can find examples with 8 or 9 particles doing it. It's incredibly beautiful. But you would have 1,000 particles all coming in and going out around their center of mass, their common center of mass. Now, there's some things here that's very interesting. And actually, I will say I did actually predict it before this calculation was made. If you look at this, so we're going to ask the complexity to be increased. Now, there's a very easy way to increase the complexity, which is just to put 2 particles on the left closer to each other. That would immediately increase the complexity. It would leave a pretty dull structure. It's very easy to see by a Boltzmann time argument. So Boltzmann's great insight with entropy was, if you have particles in a box, there are vastly more distributions of the particles which look uniform than look non-uniform. And that applies here too in shape space, because shape space is effectively a box. But the dynamics in shape space, because of that 1 extra degree of freedom, is not Hamiltonian dynamics. So it's got this striving effect in it. So this changes the story. So what you have here, and you see it very clearly, is really remarkable, is instead of getting a dull Boltzmann uniformity, you get a very structured universe. And moreover, it satisfies the Copernican principle. Basically, it looks the same everywhere. If you take a small coin, a disk, and place it anywhere down there in that image on the right, basically you will have the same sort of structure as you'll find somewhere else. And there's, and moreover, that structure there, I would say it's a creative tension, and it realizes the atomist's dream of explaining all the macroscopic shapes we see in the universe by atoms. But they did it with swerving and solid atoms that you couldn't cut in half and hooks on them and so forth like that. These are just points, shapeless points, just points in Euclidean space governed by Lair. And I would also say it's Mach's principle for shapes on steroids. So Mach's principle tells you how the local inertial frames of reference are created by the relative motions of all the masses in the universe. Here you've got something infinitely more powerful. You've got a principle which fixes the shape exactly. It's a law of the instant. The whole shape is fixed. And in one of these things, everything is fixed, where every particle, all of its neighbors and how far the neighbors are away. And moreover, the same sort of thing is going to happen even if it isn't a central configuration, because you're always going to have that conflict between increasing the complexity, the creative tension between increasing the complexity, but at the same time, the Boltzmann effect, meaning that it's got to look the same everywhere. So you will go on going up like that. Now, there might even be, there's an interesting thing here, there might just be an explanation for non-Euclidean geometry, which is what Poincaré suggested. Poincaré argued that you can't just think about geometry on its own. You have to think about it, you have to specify geometry and the forces that act within that thing. And his argument was that maybe we would misinterpret Euclidean space for non-Euclidean space because of the effect of the forces. And Einstein has a nice paper on this from 1921. I think he says that sub spatiae eternitatis, Poincaré is right. From the perspective of eternity, Poincaré is right. So maybe it's just there, because if you look, where you get a whole lot of particles together, close together, the separations between them are less than when they're not close to each other. So if you take the separations as being the measuring rods, that's just what you get in Einstein's theory of gravity near the sun, where measuring rods seem to be shorter, closer to the sun. So this is very speculative. Sorry. Ah, yes. So now just how I would define the Shannon entropy. Just take the largest separation in Manuel's thing on the right and the shortest separation, divide them. Oh, by the way, just one other thing which was predicted was that all the shortest separations in the great bulk of all the shapes with a given complexity, all the shortest separations would be about the same. And this is exactly what you see in both of those, actually. And in 3 dimensions, it's even more accurate. So now take the shape, take the largest separation, the smallest, and that range there, divide it up into equal intervals, and those are bins for making a Shannon type entropy. And then you just look at all the 2 particle separations, measure them and put them in the according bins like that. And that'll give you a distribution of the things. And if it's a very dull one created by just in the left-hand central configuration, just putting 2 particles close to each other, the bin that has the smallest separation will only have 1 in. And that will tell you that you've got a non-Copernican universe. However, the one you're looking at there, my guess is that it will peak somewhere in the middle, and that will tell you that you've got a Copernican one. So my second state function is the Copernicity of there. And so the shapes with greatest interest will have a high Copernicity. And I do like checking etymology. The etymology of interest comes from to differ, to be important. All of this story actually came from a challenge that Pedro Ferreira, who apologizes for not being here today, but he's largely responsible for a lot of this, because he challenged Tim Kozlowski and myself to find an alternative to inflation in Newtonian n-body theory. And bit by bit, this drove us to consider these fabulous central configurations. So basically, the top left is close to the absolute minimum of the complexity. That's very uniform. That would be the Big Bang. It's not a point. It's not where everything collapsed onto each other. It's a very, very uniform shape if the Newtonian theory is a guide. And there's some hope that the Newton one is right. Now, bottom right, that's a glassy distribution, or to the eye, it looks like what's called the Harrison-Zeldovich spectrum. And this is the sort of shape that you get, which is the supreme triumph of inflation theory at the moment, from which all structure in the universe is supposed to come at the moment. Now, inflationary theory does have its issues about whether it's right or not. But basically, I think you'll agree with me that if you start at the top left and increase the complexity, you're likely to come next to the one bottom right, which at least to the eye, without sort of doing all the Fourier transform to check what really is likely to come out, and it's much too early to say that, is actually like the key thing in cosmology, the Harrison-Zeldovich spectrum, from which all structure is believed to arise. Then left is a Poisson distribution. That's where particles just land at random and they come there. And a Poisson distribution is characterized by the fact that you get close coincidences, implausible coincidences, like those 2 unfortunate Malaysian planes, one that disappeared and one that was shot down within a couple of months of each other. That was typical Poisson distribution. And this just means that a Poisson distribution is going to be, if complexity is time, it's going to be in the very distant future. Oh, I don't know why that gap is there. Right, now, Simon, I've been talking for nearly an hour.
Yes.
Shall we take a pause? Because now I'm going to get on to the outrageous part, which...
I think it would be better for you to finish, actually.
All right, okay, all right, I'll press on. Let me take a bit more water.
Right.
I'm glad you're allowing me to have the outrageous part.
Well, we've had it.
You what?
I didn't think we'd had it to arrange. It's getting different.
You've seen nothing. Now this is hugely speculative. However, what I'm sure about, by the way, let me say I've been reading with immense pleasure this book that was created basically quite a bit of here in Oxford, Quantum Theory at the Crossroads, mainly trying to make the case for the de Broglie-Bohm explanation, Guido Bacigalupi and Anthony Valentini. I'm hugely enjoying reading it. Just how the founding fathers were struggling with understanding quantum mechanics. But one thing which comes out very clearly in this, they created quantum mechanics, and you look through the founding papers, you will not see a trace of a Machian intuition at work. And it's very strange because, well, the only exception, it looks like, is the single sentence abstract of Heisenberg paper. The present paper seeks to establish a basis for theoretical quantum mechanics founded exclusively upon relationships between quantities which in principle are observable. That, in fact, I think he was stimulated by Mach to do that. However, these are quantities which are observed in the laboratory. You will not find anywhere, I think, in any of the founding papers of quantum mechanics, a trace of Machian intuition, which is odd because Einstein had spent a huge amount of time trying to implement Mach's ideas. And in fact, Schrödinger, only 8 months or so before he created wave mechanics, had actually written a rather nice paper on Mach's principle. But he shies away from anything like that when it comes to quantum mechanics. He does, because of de Broglie's work, he was forced to create his wave mechanics in the configuration, well, for non-relativistic, in the configuration space, but it's not the relative configuration space. And he really doesn't seem to want to touch that wretched configuration space. He just wants things in space, in ordinary good old space. And very touching, Lorentz says, I just want things in space and time. I want a clear picture of them. You know, it's completely un-Machian. I mean, I don't think these guys had read Leibniz. I mean, you know, just look at Leibniz and that would have given them second thoughts, I hope. So my outrageous idea is that the conjecture is that a Machian universe creates quantum facts in subsystems. And let me just try and justify that. So this is the first suggestion, quantum without quantum. So there's a partial analogy between the time-independent Schrödinger equation. What does that do? That doesn't contain time, and it gives probabilities for configurations. And the probabilities are brought in through the Born density. That isn't inherent in the theory. Now, if you fix a value of the shape complexity, it gives you probabilities for shapes, and the probability is already there in the theory, in the very foundations, because it's that natural metric that I told you about. There will be very, very few shapes that are not Copernican. There will be a great many that are Copernican, and basically using this idea of a sort of Shannon type entropy, you'll be able to find out the probabilities for the shapes that have a particular value of their Shannon entropy. And all that structure is sitting straight there in the theory that I presented there. Moreover, there's no boundary conditions at infinity. I mean, I've just been reading Schrödinger, where he points out that his time-independent equation needs boundary conditions at infinity. That's what actually brings in all the complete structure, I believe, of Hilbert space and everything like that, and the orthogonality of the eigenfunctions. I suspect this is something to do with subsystems, or it could be. We are developing this weekend I had with my collaborators 2 weeks ago. We have got some tentative ideas about how the time-independent Schrödinger equation might be emergent for subsystems, and also Planck's constant. We've got ideas about how Planck's constant should come in. In fact, everything, all the Planck units and the Planck constant should actually, if these ideas are right, really just come out of the complexity. So the inverse of the complexity is the size of the universe. The Planck time would be the difference between the current complexity and the minimal value of the complexity. Basically, I think everything should come out of that. And in the same way, you should get a Planck. This is all assuming, of course, this is going in the right direction. Now, if you look at this thing, you very soon see that if you just look at a small part of it, suppose you take a coin or you take a piece of paper with a hole in it and you place it anywhere on Manuel's one on the right, and then you can see what's in there. And then you say, can from what I see in that hole predict what I'll see when I lift the paper and see a bit further or enlarge the hole? What will I see there? Well, you just look at that and you can see it's obvious you'll be able to make pretty good predictions because you've got these incredible filaments that go on there. So that if you've got 3 or 4 particles that are lined up that with a little curve, you say, oh, I double the size of my hole, I'll find that that filament goes further and you'll have probabilities for it. Or you say, let's look at where there's a complete loop, where there's the filament joins up and you can go around and come back to where you were. What's the chance that there'll be one single particle sitting in the middle when I look there? So these are priors and non-local predictions. So could it be, suppose that the prior was the setup for a 2-slit experiment? And you just saw the setup. And then you looked a bit further and you see, lo and behold, there's a screen with interference pattern on it. That's not so implausible when you look at that picture that the one on the right that Manuel had. And in principle, exactly the same could be for entanglement and the Bell-type inequalities. The priors would be the system that creates the entangled particles in the conventional way one thinks about these things. And then there would be the magnets at different angles. And then those would be the priors. And then the check would be to see what's happened there. And maybe that could be there. Now, reading de Bohm's wonderfully clear papers and so much of what the quantum fathers were saying, they were all thinking about these things coming about in time. Well, at times Schrödinger doesn't. He does think that maybe it's all sitting in a given instant in a solution of his time-independent Schrödinger equation. But maybe that's the wrong way. Maybe the explanation of entanglement and all of these things is just sitting in one single shape, that it's just the law that determines the most probable shapes. There may be shapes in which these things, the quantum predictions, don't hold, but if they're extremely unlikely, we won't be in them. And we won't be in them because they're not rich enough to have something like that. By the way, the oclo-natural reactor, which went off, whatever it was, 2 billion years ago or something in Gambia, that's a classic example. That I imagine it was discovered when they found that there wasn't quite enough uranium-235 in the rocks that they were mining there. When they looked a bit further, they found evidence of these tracks of alpha particles from the decay, which confirmed the thing there. So that's a classic example. But is there a law? Is there a law that just creates such shapes? I don't think it's impossible. It's logically possible. And consciousness, suppose, now for the philosophers, hope I'm using the word properly, suppose consciousness supervenes on shapes with a given value of the complexity. Well, am I using it right? Yeah, okay. Now I've got a great quote from John Bell. We have no access to the past. We have only our memories and records. But these memories and records are in fact present phenomena. The instantaneous configuration of the particles, the X's, can include clusters, which are markings in notebooks. The theory should account for the present correlations between these present phenomena. I think that's, we could be, as we sit here, we could be in that, make it a bit richer, that pattern on the right of Manuel's, and we could be sitting there all created in an instant. Now, getting near the end. Now, 2 Italians produced a remarkable paper about the n-body problem, published in 2015. And it says, basically what it says is the following. If I'm interpreting it right, by the way, this is not fully confirmed, but I think it's right. What they're saying is that given any, for any n, given any shape and a central configuration which is either unique or has the absolute minimum value. So there may be quite a lot that have the same absolute minimum value. What they say is you can go, there is the Newtonian solution which goes, well, they put it in terms of a configuration that goes from that configuration without any collisions happening, and it terminates, it goes, and it essentially comes to an end with parabolic escape. So all the particles have got to infinity and they're at rest. Now, if you turn that round, that's a total explosion with energy 0 and angular momentum 0. So in their statement, they call that a minimizing normalized central configuration. That means a central configuration that's got the absolute minimum value of the complexity. So this would be my alpha. And there's a certain, so first of all, I think these solutions, I've already suggested that these parabolic escape solutions are just a tiny, tiny subset of Newton's solutions that bear no trace of any absolute structure, despite being Newtonian solutions. And moreover, very interestingly, the ones that come from the absolute minimum go to every shape. So this is a certain completeness, a perfection of the theory. So the argument is, so a lot of people would say, now, Julian, you're just choosing a tiny, tiny subset of Newton's solutions to make your point. But I could turn around and say, no, the law of the universe is only those solutions which derive from that magical quantity, the Newton potential made scale invariant, the shape potential or the complexity, only those solutions for which there's no trace of absolute, and that's it there. So that would be really rather nice if that's the case. So there's my conjectured law. A unique, MV stands for those 2 Italians, solution connects alpha to any shape. Here's another one with etymology. Creation, the word creation has nothing to do with creatio ex nihilo. It comes from Proto-Indo-European cur, meaning to grow. So alpha is the maximally uniform soil from which plants and trees grow. I've already said there is some issue about monotonicity of the increase of the complexity, but I don't think that's a huge issue. Nearly there. Let me finish with a few quotations. I think, no, it's a little bit more. Bear with me, Simon. All of this came about from me reading Leibniz back in 1977 and being very struck by this. This is the means of obtaining as much variety as possible, but with the greatest order possible. That is to say, it is the means of obtaining as much perfection as possible, completion in that. And then he also says, each portion of matter may be conceived as a garden full of plants and as a pond full of fish. But every branch of each plant, every member of each animal, and every drop of their liquid parts is itself likewise a similar garden or pond. Now that sounds rather like fractal self-similar, but this is not what is happening in this case because the structure changes. Now, if you don't increase the number of particles, the number of central configurations seems to come to an end. And then not much more would happen if the number of particles is fixed. But if the number of particles can go on, I don't think there's any end to the different kinds of structure that could be created. So it wouldn't be self-similar, and it could conceivably implement that famous paragraph 67 of the monadology. So the only paper, so Lee Smolin is, Bartlett was a lot responsible for me having such an interest in maximal variety. That's our only joint paper together. But Lee's idea was based on Leibniz's comment. It is as if there were as many different universes, which are, however, but different perspectives of a single universe in accordance with the different points of view of each monad. I think that can be worked into these shapes, what they look like from each point as you look out the angles there. But so from about 2011, having discussions with Alain and Bowie in Paris, I came to think that rather than views that Lee had developed, looking at the shape complexity was the way forward. Nearly there. I think I won't bother about the shape functions. I've already spoken about that. Just the last thing is, well, penultimate, nearly. We're nearly there, patience. So the dominant thing is the law of the instant that determines the probabilities of shape. So as you go out on any of the isocomplexity surfaces, virtually there are very few dull shapes, just by this, the way that Boltzmann comes in creatively with the increase of complexity. And then, so then there will be some, so there's two explanations for any shape that you find. So as you wander around an isocomplexity surface, you'll keep on finding interesting shapes. They'll be there. And then you'll find that, lo and behold, there's one of these n-body solutions that Madonna and Venturelli found that comes from alpha, from the most uniform shape, that comes up to that point there. And well, there are fine-tuning issues there, but I don't want to go into them. Very nearly at the end. Consciousness, solipsism, and Boltzmann brains. So John Bell also said, Everett's replacement of the past by memories is a radical solipsism, extending to the temporal dimension the replacement of everything outside my head by my impressions. Well, I think this offers hope that it isn't solipsistic here, because I talked about that coin, putting it down anywhere in that shape there. So if you put it down and you say, where that coin lands, that's my head. What I've got in my head, in my consciousness, by psychophysical parallelism, is a faithful reflection of what the whole universe is like. And this is completely different from Boltzmann brains, where my brain just fluctuates into existence and thinks it's in this fascinating universe, but really it's sitting in thermal equilibrium. So this is definitely not going to have any problems with Boltzmann brains, and I think it's going to relieve Bell's problems. And I think this is another quotation I found from Maxwell. The only laws of matter are those that our minds must fabricate, and the only laws of mind are fabricated for it by matter. I'm not sure that one can get better than that now. So this is my last line. So quantum possibilities. First of all, the uncertainty principle caused great dismay because half of the normal degrees of freedom of classical physics seem to disappear. This inverts it, because if the idea with the Madonna-Venturelli solutions is right, give me a shape, just one shape, and I can tell you the whole classical history. It inverts the uncertainty principle, but it's got to be done with the whole universe. So this is about as Machian and Leibnizian as it gets. So there's a kind of complementarity here. So there are two explanations for why we're in the shape we are now. One, and it's the more fundamental one, I believe, it's because fixing the complexity is like finding a is rather like getting a solution to the time-independent Schrödinger equation. So there's an instantaneous explanation of why we are here that doesn't involve time at all. But then lo and behold, there seems to be a classical solution which connects this incredibly rich structure around us down to the most uniform shape that the universe could have. I think most of these solutions, the Italian solutions, will lead to striking time capsules. So finally, this is the really outrageous one, Simon, for you. If this is right, the measurement problem, the collapse of the wave function, is solved. There is no wave function. So I'll finish with that.